So hello everyone, thanks Brian, thanks Gita. It was a badass contest, I agree. And let me tell you how I won the APL Problem Solving Competition 2020. So I'm here in Ukraine, sorry for my Ukrainian accent. A little bit about myself, I have been programming since the age of 9. Sorry if I'm a little bit shy on camera, so if I break talking, just read the slides and I will be silent. So my first programming languages were QBasic and Fox Pro, and occasionally I participate in programming contests since high school. And after 10 years of programming software development experience, I decided to study one more year in the University of Hong Kong to get a master's degree. Currently, I work as an embedded software engineer, so I mostly work in C++, C, and Python. But my newest favorite is APL. And how I learned about it is I learned in 2007 when I was an undergraduate student of Taras Shevchenko National University of Kiev, and many of my friends were working for SimCorp Ukraine, and they told me about this exotic language from 1960s that they use, and I was very interested because I like to study languages since young age. And I didn't have a chance to study it then. And in 2019, I finally noticed APL solutions on Code Gulf Stack Exchange. It didn't occur to me that this is the same APL that I wanted to learn. And finally, this year, while I was working on my master's thesis in the mid-June, I learned about this competition from Katis and immediately decided to participate because this was the language that I wanted to learn for so long. So I'm still a newbie, but APL has already influenced the way I write code in C++ and Python. So recently I learned that C++ has IOTA function. Just what I think about this competition, it's unlike ICPC style programming contests, which I'm used to since high school. This is a long-term programming competition, the type of programming competition that I strongly like. Strongly prefer, and style, unlike any other programming competitions that I know, style of your code influences the chances to win. So it has two phases. I won the second phase, and the second phase consisted of 3 categories of problems. In my opinion, it had one-liner problems, scripting style problems, and performance style problems, meaning that the selection of algorithm and implementation greatly influences how much time, CPU time, your code takes, unlike in scripting style problems, which are just more straightforward. So to answer the topic of this talk quickly, how I won this competition, I was concentrated on performance. So my logic was that since I'm new to the language, this is the only measure that I can objectively measure at home. And I was thinking that more native code is usually more fast and vice versa. So writing native code is synergistic with being efficient. So I was profiling my code extensively with CMPX function. And I tried to imitate good coding style by reading APL papers, APL books, and websites, and getting idioms from such websites as APL Card and APL Wiki. And of course, I also implemented unit tests and performance tests to be able to quickly experiment with different solutions, different approaches. So for the sake of completeness, I included my phase 1 solutions. Phase 1 is just, in my opinion, it gets you hooked on APL quickly and teaches you some APL. So in phase 1, I was concentrated not so much on performance, but on conciseness. So here, for example, I know this problem 6 solution is not optimal, but I just submitted it because it's shorter. And of course, my solutions are not, there are some better solutions. I saw, for example, this one for problem 8 due to a participant who goes by nickname RAC1507. So there were some brilliant people, and I will present some solutions that I liked by other people in this presentation as well. So let's get into problem 2, phase 2. Problem 1 was a one-liner solution. Basically, you are given a vector of integers, 3, 5, or 7 integers, and you need to find 3 in the middle, sum them up, and multiply by difficulty score. And the solution is very straightforward. Here, I calculate the number of outliers, take 3 numbers in the middle, and if you don't know what this is a tested function, a special feature of Dyalog APL to do rounding. So in problem 2 was an extension of problem 5 from phase 1. And so it's basically an extension of a one-line problem to 3 more cases. So my solution is structured exactly like that. I had 4 independent one-liner solutions grouped together into a single function. Problem 3 is a scripting style problem. Basically, you are given a URL of a web page, and you are asked to find all links to PDF files in that web page. So as a classic scripting style problem that you typically do with such languages as Perl or Python. And what is the catch in this problem? I think it was important. The trap in this problem is there is a big temptation to go to this web page that is mentioned in the problem statement itself and see how it's structured, and quickly hack an ad hoc solution that will work for this specific format. However, nothing in the problem statement says that the format will not change of that web page. So I think it was important to do it right. And of course, do it right is not to do it through regular expressions, but to use XML parser. So do it properly. Because if you did it with XML with regular expressions, then your solution could be potentially broken by addition of these lines to the web page. So here's my entire solution. First, in the first line, I download the web page and parse it with XML. Then I have a function which gets all hyperreference attributes of a certain kinds of tags, and I apply it to A and base tags as suggested in the problem statement itself. One thing to notice here is that as a software engineer with experience, I always try to make my solutions resilient to different kinds of inputs. So it's important to handle all possible errors and edge cases. So these 2 lines are aimed to process correctly as an empty web page. Problem 4, bioinformatics, my favorite topic. This problem consisted of 2 tasks. And in the first task, you are given a DNA string, and you are asked to find reverse palindromes of lengths 4 to 12. And reverse palindromes is a section of DNA that matches the reverse of its complement. And complement is, of course, a string that swaps A for T's and vice versa, and C for G's and vice versa. So what is the catch here? I think it was, again, I think it was important to process, to not make assumptions that are not in the problem statement about the input. So don't make an assumption that DNA will be longer than 11 characters. And also there is, it was important to notice that reverse palindromes of odd lengths do not exist. So by simply observing this fact and not searching for odd lengths palindromes, you are saving up to 50% of your CPU time. So here's my entire solution. First, I have this paranoia about the input being too short. Then I have a function which checks if a string is a reverse palindrome. Then a function which breaks DNA into substrings of certain lengths and checks all the substrings if it's a reverse palindrome. And then I do some calculations to find the length that needs to be checked. So this is important when the input string is shorter than 12 characters. So, but typically this entire expression is just 4, 6, 8, 10, 12 for long DNAs. I was pretty happy with this solution, even though I felt that it's not optimal. I felt that there is a better solution to do it, a better algorithm. And I was happy to find a better solution on GitHub by contestant Sam Weiss. And his solution, this solution works 10 times faster than my solution. I tried to understand how it works, but I couldn't, even though I tried a few times. So if you are interested, you can check it out. Task 2 of this problem is a classical problem. You are given a set of n distinct numbers, and you are asked how many subsets exist of that set. Of course, the mathematical answer is trivial. It's 2 to the power of n. But here you are asked to find the solution model 1 million. And one straightforward way to do it is to define a function multiplied by 2, take model 1 million, and apply it n times to value 1. And the time complexity here is linear. But of course, there is a better way to do it. It's called exponentiation by squaring. So here's my entire solution. It has a logarithmic time complexity, and it's important to notice why it works. So it's important to notice because we are taking modulo 1 million at each step. The 1 million is 20 bits long. And by squaring and multiplying by 2, we are making any intermediate value up to 41 bits long. And 41 bits fits nicely into 52-bit fractional part of double precision floating point numbers, which are used in Dyalog APL. So even if Dyalog APL chooses to evaluate this function in floating point numbers, then we still arrive to precise solution. Problem 5 is a financial problem. You are given a cash flow and interest rates. If you don't know what cash flow is, basically you have some initial money in your banking account, and you have a schedule for how will you use the money. Will you put some money in or take some money out in the future months? And you also have interest rates for the future months, which will be accumulated for your current balance. So it's a trivial problem in any programming language that has loops. However, this note right here says that you are not expected to use looping solutions. So I scratched my head. I was thinking what non-looping means, and I came to conclusions that probably authors of the problems meant array-based solution. So I came up with this array-based solution. And of course, this is really beautiful. And this is just a showcase for me why APL is such a popular language among financial software companies, because I felt like I am just, I'm using Excel. It's just as easy or even easier to use an Excel, and basically just by typing simple operations on arrays directly. It's just very easy and beautiful, and I miss this functionality in other languages. So how it works? First, I calculate accumulated interest rate. Then I divide amounts by this accumulated interest rate to find the present values of each amount. Then I accumulate present values and multiply back by accumulated interest rate to find future values. So it's extremely fast. It has linear time and space complexity, and but I don't like it because this solution has division. So I submitted this solution only because it's an array-based solution. It looks nice, but in production I would use this recurrent solution which avoids division. It's slightly more slower and slightly more complex, but it avoids division, and division is to be avoided where it's unnecessary. So task 2 of this problem is a similar problem. You have a cash flow and you have interest rates, but here you are asked to find present value of your cash flow. So what is meant is that you need a value to evaluate different schedules. For example, is it better to take out $100 out of your bank account next month immediately, or to take out $20 each month for 5 months? And a way to do it is like this. It looks like a simplified version of the previous solution. So again, I calculate accumulated interest rate. Again, I find present values of each amount, but then I just add all the present values to find the present value of the entire cash flow. So very straightforward. Problem 6 is a scripting style problem again. The setting is that you want to send emails to different people, and you have a template for that email. And there are some personalized data in JSON files. So the data comes from JSON, and you need to replace values from JSON into your template before sending the email. So here's my entire solution. In first 2 lines, I read the JSON file into a namespace and find all the names of the fields in that namespace. And then here I read the template into variable, and I find partitioning based on Dyalog 18 partition function. And I find the partition based on positions of add signs. And then I do a little trick. I decrement partition values at positions of every other sign. And then I have a function which just replaces all strings which start and end with an add sign, which means that it is a template name. Otherwise, leaves it as it is. So this solution again is straightforward in my opinion, and works nicely. However, there is a more elegant solution by another contestant, and it's just beautiful. I just enjoy it. So conceptually similar. Problem 7 is a UPC barcode problem. So if you don't know what UPC barcode is, it looks something like this, and we all know them from the stuff we buy in supermarket. So task 1 was to find the check digit of 11 digits of the UPC barcode, because UPC barcode represents 11 digits plus a check digit. So it's a very straightforward one-liner solution. Just comes from the definition of that check digit. And task 2 is in task 3 you need to generate the actual barcode. So barcode is represented by 95 bits, which encode black and white stripes. So problem 7 was also unique because it explicitly stated that you need to check for all the errors. So unlike in other problems, I try to check for all the errors myself. But here, the hardest part, I think, in this problem is to think about all the possible errors. And here I have 2 lines for checking errors and 3 lines to do the actual encoding. And in task 3, it's a reverse operation. You are given a barcode and 95 bits, and then you need to return 12 digits. So here's my entire solution. Here I have 6 lines to check for errors and 3 lines again to do the actual decoding. And finally, my favorite problem, because I spent the most time on it, and I have a very thorough solution. So it's called balancing the scales, and the setting is like this. You are given an integer vector of up to 20 elements, and you need to split the vector into 2 halves, into 2 parts, so that their sums are exactly the same. So if the numbers are positive, then you can imagine it with scales, like scales. You are given weights, and you need to place all the weights on the scale so that the scales are in balance. However, I think this is a trap. A catch here is that nothing in the problem statement says that the numbers cannot be negative. So you need to account for that. And also, of course, it's a classical problem. It's called number partitioning problem. And it's a special case of subset sum problem. So it has lots of existing literature and lots of existing methods how to do it. So I implemented all of these 4 algorithms, and I will explain to you in great detail. So buckle up, we still have some time. And the first algorithm is, of course, straightforward solution. It's a brute force solution. You simply multiply your vector by all the Boolean masks of z lengths. So basically, you multiply a vector by matrix, and you have all possible sums of subsets, and you just need to look for half of the total sum to find the solution. And one optimization here is you need to observe that you kind of do it twice. And to avoid doing this, you can just assume that the first weight or first number will go into first part. And in this way, you need to consider only 19 number vector. And by simply doing this optimization, you decrease your running CPU time by 50%. So it has the benefit of this method of brute force algorithm is that it works very fast for small vectors, because APL, of course, is very well optimized to multiply vectors by Boolean array. And but the disadvantage is that it's still exponential time complexity. So by addition of each additional number, you take twice more time in your CPU. So here is my entire implementation. It's very straightforward. And then, of course, there are better solutions for specific cases. For example, dynamic programming solution. As usual in dynamic programming, you solve your problem by constructing a matrix. And here, the matrix that you need to construct is like this. You have one row for each possible sum from 0 to t, where t is the maximum, is the total sum of the original vector. And you have a column for each additional number considered from the original vector. So the benefit of this algorithm is that it works very fast for small numbers, and it has predictable running time, t by n, where t is the sum of all numbers. But the disadvantage, of course, is that it depends on the value of the numbers, and for large numbers, it will not work. And it also doesn't work for negative numbers. So here's my entire implementation of dynamic programming solution. And what I like about it is that it's really neat in direct functions in APL. I think just looks quite elegant in my opinion. And one thing to notice here is that first I implemented this algorithm in traditional functions, just in loops, but simply translating to dynamic programming to direct functions makes it much faster. So one advice for future contestants is avoid traditional functions. And of course, and the next algorithm for this problem is a recursive branch and bound algorithm with greedy heuristic. So this algorithm is very straightforward. It's kind of like a knapsack problem, and the benefit of this algorithm is in practice it works faster than dynamic programming solution. So I didn't use dynamic programming implementation. I just switched to recursive when I learned that it is faster. And it has the same disadvantages. Running time depends on magnitude of numbers, and it doesn't work for negative numbers. So here's entire implementation of this approach. And final algorithm for this problem is Horowitz-Sahni optimization. So the idea is very simple conceptually. It was published in 1974, I think, by Horowitz-Sahni in their joint paper. And the idea is like this: you just you take your input vector and you break it into two halves randomly. And you solve each half independently using brute force approach. So as a result, you have two vectors of all possible sums in those two halves. And then you sort those vectors and start from the beginning of one and the ending of another. And you, in linear time, you can match them. You can find if there is a match so that sums of these sums adds up to half of the total sum. So the idea is very simple, but the disadvantage of this approach is that it still takes quite some time for it takes constant time for all the vectors. And advantage is that, for example, you can solve twice longer vectors with this approach. For example, if brute force approach works in reasonable time for 23 numbers, then this approach will work for 46 numbers, which is a great improvement over the original requirement for 20 numbers. So here's the entire implementation of this approach. But my final solution is a combination of three algorithms that I just presented. And one optimization, I divide the input by their GCD. And in this way, I can quickly reject many inputs which have odd sum. And of course, odd sum cannot be split evenly into two halves. So here's my final combined solution. And I think this is why I like long-term programming competitions, because unlike in quick competitions which take only 2 hours, you have the time to go to the literature, you have the time to do all the homework, and you have the time to study it and then engineer a good, beautiful solution that works for all possible cases. So similar to how I do software engineering in real life. And the last problem is called upwardly mobile. It's a tree problem. It was announced as a hardest problem, but I disagree with that. I think it's very straightforward in APL. So in this problem, you are given a diagram of a mobile, and the mobile is a structure of thin threads and thin wires and weights. So weights are represented by letters here, and you need to accounting for the length of all the wires. Wires are horizontal parts. Accounting for the length of those wires, you need to calculate the length which will make the entire structure in balance. So the solution is very straightforward. I just take the diagram into a 2D matrix and parse the 2D matrix to get a matrix which represents the system of n unknowns of linear equations, and just solve that system of linear equations by taking the inverse of the matrix. And yeah, in APL, it's very straightforward. The only optimization that I did here is I removed all repeating lines which have only spaces and vertical bars. So in that way, because these lines do not bring any useful information, and in In this way, I reduce the chance of being out of memory. And here is my entire solution. Here is the first half of it. So in the first line, I just find all the repeating lines and just read all the lines from the file. And then I drop these lines and format the diagram into a 2D matrix, 2D character matrix. And then I find all the distinct weight names into variable n. And then I initialize my coefficients matrix with 1 in the first column, so that it kind of shows that I want my weight A to be 1 provisionally. And then I have a recursive function descent, which parses the input vertically and calls a function explore. And explore is a function that parses the input horizontally and calls function descent. So these are recursive functions, recursive parsing. And finally, I find the topmost link and start from there to do the parsing. And then all the mathematics is done in the very last line, where I take the inverse of the matrix, take its first column, which is a solution to this problem. But then I apply also a generalized GCD to convert this solution into an integer solution. So very straightforward and quite easy. Finally, here are some advice for future contestants. Just write the code that is fast, study algorithms, because my personal experience is that I had 3 problems at least where algorithms were very important for my elegant solutions or fast solutions. And ensure that your code has good style and lots of comments. Write it in kind of like literate programming style to make it enjoyable to read as a literature. And look for idioms at Apple Cart Info, a great website. I think I miss something similar in other programming languages. I think it's quite unique for APL. And of course, ensure correctness. Just write unit tests and use boxing on trains 3. It will explain to you how tacit functions work. And here are some links to my repository and repository by people whose solutions I also presented today. So thanks everyone. Thanks for this great opportunity. It was lots of fun. So yeah, if there are any questions, I'm ready to answer. I think we have some time.
Yes, Andrii, there's a question from Rory Kemp, and he says, do you think APL has any potential to be used in competitive competitions like the ones you mentioned?
Yeah, I believe so, because even now in the, for example, a website called Forces, a Russian website for competitive programming where competitions are held regularly, there are contestants frequently use different languages for different problems. So for example, if some problem is easy to solve is trivial to solve in Python, people use Python because Python has built-in long arithmetic. But if something needs performance, people use C++. So APL has certain kinds of problems, like I just showed the cash flow problem, where it just doesn't have any competition in algo style programming languages. It's because it's so easy to work with arrays. And also I must say that APL was very useful for me during my master's degree studies, because we were, for example, studying signal processing, and we were implementing fast Fourier transform. And some people would code everything in 40 lines of Java. And I would have like a few lines of APL, and people would be impressed because the APL is so expressive, like especially if you have some mathematical operations. And it's just much easier to understand such complex concepts like fast Fourier transform if you have the short APL implementation and you did it yourself. So definitely APL has just its unique niche that it doesn't have any competition like in algo style programming languages.
Right, and there's probably more comment than questions. I find your problem solutions to be quite elegant, well thought out, and simple to explain to others. Good stuff. Tell us a bit about how you came to those insights.
So it depends. Like for problem A,
yeah, you might be able to see the questions.
I see. So problem 8 is I just went to Wikipedia. So I didn't know how to solve this problem before the contest. I didn't know this different algorithm, except for, of course, recursive solution or the trivial brute force solution. So I just went to Wikipedia and carefully read all the papers on these classical problems, and basically just tried it out, and also went to references. It's important to not only study Wikipedia itself, because Wikipedia is not perfect. There are mistakes. It's important to go to the original papers and read them as well. And for example, for financial problem, it was some insight came from the financial programming course that I had just this year, basically. And yeah, it depends. And you just generally need to study algorithms. Like we software engineer, we study algorithms in our preparation. So I think we need to study algorithms to come up to elegant solutions.
Well, it does warm my heart that somebody actually goes and studies the literature for solutions. So let's see. Yeah, I don't think there's any more real questions.
David Velez says,
yeah.
So I can answer that. I work in Hong Kong, actually. So I don't know what people use in Ukraine, but I know that SimCorp Ukraine used APL when I was an undergrad. So I don't know right now. And yeah, other than SimCorp, I don't know who uses APL.
No, I think, I mean, SimCorp is still using APL in Ukraine to quite a large extent. Yeah. Yeah, okay. I think we should say thank you. And there's now a break until 4:30
Thank you very much.